Rica French. I'm an astronomer at Miracosta College in Oceanside, California. I'm also the Associate Director of the Center for Astronomy Education. And I'm also proud to be sponsored, at least in part, by the Neuroverse Initiative. So I'm here to talk to you about your universe. So let's get this show on the road here. And screen share. All right. So what are we going to talk about? That's a good question. So it's a big universe. There's a lot of stuff to talk about. So, all right, I want to start us with, make sure everybody knows what we're talking about. Now, if you've seen part of this before, bear with me here, but hopefully most of us are on planet Earth. Actually, not hopefully. I'm kind of hoping some of you are not on Earth. And if you're not, then we should chat later on. So let me know that. Earth is a regular old planet. We love it. It's ours. It turns out we're going to be kind of a weirdo as far as planets go. We orbit the sun. The sun's a rather ordinary star. We have some strong feelings for it because it's ours. It helps keep us alive, of course. But it is rather ordinary in the world of stars. But when you put us and the other planets and some comets and asteroids together in a gravitationally bound system, we make a solar system. And I want to pause for a moment to highlight a couple of things in the solar system and kind of rewind us back to not that long ago, maybe only a couple of 100 years ago, 200-300 years ago, when the solar system was kind of it. I mean, when we say the word universe right now, we take it for granted what we mean when we say universe. Pictures of galaxies pop into our head, these amazing galaxy clusters and things that we see from these amazing space telescopes and that we see on these science shows on TV. And that's not at all what people had in their minds when you said universe as recently as a couple 100 years ago. It was pretty much everything that you could see in the sky. We had some reasonable sized telescopes, but a few galaxies. But they didn't know that there were other galaxies. They didn't know that they were actually that far away. They didn't know what far actually meant. So their definitions of far, and actually some of us, your definitions of far are going to have to get upgraded. In my class, I say things like scary far because it really is, because people have really no concept of the scale that we're working with here. So I do want to mention very quickly the planet Uranus. If you are hanging with the science talks for the rest of Virtual TrekCon, then you will hear more information about the planet Uranus. Also, our friend planet Saturn has a moon named Titan. It is the second biggest moon in our solar system, and it's actually the only one in our solar system that has a substantial atmosphere. And then there's our friend Mars. We're going to come back to Mars in a moment, but I want to get you warmed up with Uranus is the planet that sits all the way dumped over on its side. So a lot of people know that Earth sits on an axis that's tilted roughly 23.5 degrees. Uranus sits at a little over 90. It's about 97 degrees. This is an infrared photograph made by the James Webb Space Telescope, which henceforth shall be known as JWEST. So an infrared image, so definitely not what you would see with your eyes. I don't want to give too much away, though, because along with Titan, all of these pictures in the ring right here, all of these are Titan. The one in the middle, the yellow one, that's about natural color. That's what you would see with the unaided eye. And that was the only thing we knew about Titan for a really, really long time. In fact, all of these pictures that go around it, those are radar images that are false colors based on relief and what we believe are areas that have higher and lower reflectivities. And we didn't even know any of that was there until the Cassini probe visited Saturn and dropped the Huygens probe actually down through that fuzzy yellow gunk that you see there, and it actually landed on a solid surface. And that's an actual photograph now of what the Huygens probe saw when it landed on Titan. So we found out, hey, it actually does have a surface. Looks kind of rocky, looks seriously hazy. So what you're seeing in, again, all these other pictures are, we now believe, I think it's the purple stuff here, that actually are lakes of hydrocarbons. So things like ammonias and, methanes and ethanes and things like that. And there's definitely evidence of fluid flow, though. So we do think there are lakes of hydrocarbons, actual lakes in liquid form right now. But again, I'm not going to give too much away because you should come and check out Ashley's talk tomorrow. She's going to be talking about Uranus and Titan. They're cosmic outliers, and they're called the uncharted worlds because we just don't know that much about them anymore. So come find out what else is new about them by checking out Ashley's talk tomorrow. Then there's Europa, which is a moon of Jupiter. The two pictures of Europa that you see here side by side, the one on the left is pretty close to natural color. That's about what we think you would see with your unaided eye if you could actually go there. The one on the right is enhanced a little bit with some infrared data to try and so that the scientists can try to get some more details out of those images. And you'll notice that it looks like it has scars all over it. It kind of looks like a cracked surface, maybe like ice. And you would not be wrong. It actually is an icy surface that gets stressed and strained. And so like the picture down here in the corner, you see that there's a liquid reservoir underneath. When the surface gets cracked and forms these dual ridges, and the liquid upwells in between and then refreezes and causes all these fracture patterns. And we're pretty sure that's what's going on with it right now. And it causes these amazing surface features. But the fact remains that we're pretty sure that there is a liquid reservoir underneath there. And that liquid reservoir, we're almost certain now is water. This slightly unimpressive image here in the right-hand corner, this, white stuff right here that you probably wouldn't think twice about, actually, we're pretty sure that that's water being spewed out from these cracks as Europa gets stressed and strained. And if you want to know more about Europa's prospects for life, because actually here on Earth, we think life originated deep in the oceans near the volcanic vents. And it seems like Europa is a similar type environment. And so what are the prospects for life on that? Then you'll want to check out Liv and Jessica's talk tomorrow on Europa, barren wasteland or inhabited ocean. So that's kind of cool. Also, it's Valentine's Day, right? So hi, happy Valentine's Day. Love Mars. These are actual features on the surface of Mars. And we're pretty sure now that there's no complex life forms on Mars, but we know that Mars definitely had a much warmer, much wetter past. There's definitely evidence for fluid flow, and now we know that it was water. There's other fluids as well, like liquid carbon dioxide, but definitely water. In fact, the more we learn about Mars, the more evidence we find for flowing water earlier on in its history. So it's not just natural to ask the question, just in general, are we alone? It's pretty natural to ask, hey, what happened on Mars? How did it get to be the kind of seemingly dry wasteland that it is right now when it was a much warmer, wetter, inhabitable planet, or at least we think it was, early on in the history? And if you want to push it a little farther and want to talk about, aliens and what it might be like to start characterizing civilizations that might live on planets elsewhere, not even in our solar system, but other planets around other stars in our galaxies, Liv and Jess have another talk on the Kardashev scale, which is the scale we use to classify civilizations based on how technologically advanced they are in terms of the energy resources that they can harvest in their system. So that's a cool one. You don't want to miss that one either. And now I'll circle us back around to, hey, we're in the solar system, but hey, we just talked about other stars in our galaxy. There might be planets around other stars in our galaxy. We actually know there are. There's thousands and thousands of them. We know that now. I want to mention scale again really quickly because a lot of people don't have a good feel for scale. So how big are we talking about when we talk about the Milky Way galaxy? Well, there's not a lot of good analogies I can give you, but let's start somewhere. Most people know that when they flip a light switch, it seems like the light is just instantaneous. It doesn't take any time to reach your eyes. And that's not true. It's just that the speed of light is really, really fast. How fast, you ask? About 186,000 miles every second. For a little context, that's roughly the equivalent of circling planet Earth about 7.5 times every 1 second. That's how fast light goes. Now, if you let light go for about a year's worth of time, and you see how far it went, that's the unit we call a light year. So it's a unit of distance. It's quite literally how far light goes in 1 year, knowing that it goes about 186,000 miles per second. Okay, so light years, the distance that light goes in a year. Our Milky Way galaxy, from one side of it to the other side, is about 100,000 light years. So even if you could travel at the speed of light, it would take you 100,000 years to cross the galaxy. From where we are, which is actually about halfway out between the center of the galaxy and the edge, we're about halfway out. So that means even if you could travel at the speed of light, it would still take you about 26,000 years or so to get to the center of your own galaxy. So you folks out there that are working on warp drive, get on it. We've got a problem to solve, and chemical engines aren't going to do it for us. It looks like the warp drive is our most promising technology, I think, maybe. Okay, so there are other galaxies. And remember, as recently as a couple hundred years ago, we weren't sure about that. In fact, it was probably around 1924 when the debate was settled about, hey, these things that we see in these images that we take with these other telescopes, they seem like these fuzzy blobs that they're kind of like, nebulous, but they kind of look like planets and not exactly, and we don't know what to call them. They're just spiral nebulae because some of them have spiral structure. And it turns out that in about 1924, we finally had the data to be able to say, you know what, those are not things inside of our own galaxy. Those are actually other galaxies. So your definition of far needs to get upgraded to the real definition of far. When you put a bunch of those galaxies together in space, we actually form a gravitationally bound system of galaxies known as a galaxy cluster. Our galaxy cluster is called the local group, and yes, that is capitalized because that is its proper name. Astronomers are not good at naming things. Please don't ever let us name important things to you because apparently local group is the best we can do for our own galaxy cluster. Our galaxy cluster, the local group, has about, 4 or 5 dozen or so galaxies, and we keep finding more all the time because a lot of them are very small. We call them dwarf galaxies, and they're very diffuse. And the populations are actually, in some cases, being torn apart. So we're actually interacting with those galaxies. But it turns out that galaxy clusters, like the local group, want to hang out with other galaxy clusters out in space that are not gravitationally bound systems. And we call them galaxy superclusters because, clever, right? And the local capital supercluster was really its name for a while. Then we called ourselves part of the Virgo supercluster, and actually we've decided that that's probably not the best category for us. Our supercluster we think is bigger than when we were just in the Virgo supercluster. So we've now upgraded our local supercluster. Its name is Laniakea, which is Hawaiian, and it roughly translates to immense heavens. And so our local group, let's take a look at our galaxies in our local group. So over here we are in the Milky Way. That's the You Are Here spot. Some of you have heard of our friend the Andromeda Galaxy. Andromeda is actually larger and more massive than the Milky Way, just FYI. Some other things, if you're a reasonably experienced sky watcher, you might see some other galaxy names that are in there familiar to you. But again, that's 4 or 5 dozen, gravitationally bound. We all orbit the center of the galaxy cluster. And let's see here. If you take everything that you see in this picture here, local group, and you cram it into, the pictures are so big, and you cram it into, see right here where it says local group, everything you just saw in the other picture, all of that's right here. Then look at all of the other stuff. All of the white fuzz, these are galaxies and galaxy clusters. So you're already in the hundreds of thousands of galaxies in this picture right here. So these are other superclusters that now make up our grand Laniakea immense heavens supercluster. But it's going to get worse. Take a look at everything in this picture and kind of look at the large scale structure. There's kind of like this filamentary looking structure with these weird arm looking things here. And all of that is now the yellow fuzz in this picture right here. So the yellow fuzz is our Laniakea supercluster. And now the rest of the white fuzz is a whole bunch of other superclusters of galaxies. And yeah, head explode galaxies everywhere. That's exactly what we're talking about. This is actually what astronomers and cosmologists call the large-scale structure in the universe. So you have to remember, each little piece of white fuzz is a galaxy or, 100 or 1,000, or it might be 10,000 galaxies. Yeah, that's what we're talking about. And this is just a tiny little piece of the universe, the piece that, I chose to put on the slide anyway. So now I want to talk to you about a big idea. We've talked about a big universe, and this is only a tiny little fraction of it. But I want to talk to you about a big idea. Now, some of you already know where I'm going with this. A big idea that, kind of seemed like a good idea at the time, and then maybe not so much. So I gave it a different name. This is the never let reality keep you from doing something stupid talk, which is, I don't know, always good for entertainment, right? Because, apparently the reality television industry has made a whole, livelihood out of that. In order to talk about our big idea that may or may not be stupid, we need to rewind to the Hubble Space Telescope. And when I say rewind, I mean probably 1970s, 1980s. 1970s is kind of when this thing is first conceived of. By the time you get people actually putting stuff down on paper and putting proposals together and actually feeling like, no, I think we can make a proposal and we can actually try to make this work. We want to try to put this out there. So you have to rewind quite a bit of time. Then we're finally going to be able to make this thing. And I say make it because, you know, it took your tax dollars to do it. So if you're an American taxpayer, then this is probably the best bang for your buck you've probably ever gotten. The Hubble Space Telescope, for those of you that don't know, this thing is like the Timex watch of space telescopes. It has taken a licking and keeps on ticking. It has had the crap beaten out of it. And just so you know exactly how old it is and how long it's been in service, Hubble launched in April of 1990. Space Shuttle Discovery put Hubble into orbit for us. And this was a big deal, as you might imagine. It actually was not the first space telescope. In fact, we actually had quite a few space telescopes before this, but Hubble was definitely the first one of its kind. It was the biggest visible wavelength telescope ever put in orbit. And it was also designed to be serviceable, which probably everybody knows, but that's a big deal, right? It's not just, hey, we're going to send up a satellite, we're just going to leave it there to do its thing. And then when it's, you know, done and it dies, then we do a controlled re-entry, right, over some reasonably uninhabited area of the planet and then drop it in the Indian Ocean, which seems to be where our cosmic, you know, waste bin is. That's not what this was. This was a, no, it's not just a satellite. We're going to service it. So we have to be able to catch it and operate on it, take things apart and fix things. There was a little bit of a wrinkle with that, though. Some of you know that when we first opened the shutter of Hubble, astronomers call it first light. So when the optics actually sees their first ever, you know, photons from anything far away, we call it first light. And everybody waited with bated breath, and we expected to see, you know, these, oh my gosh, wow kind of images. And this is what we got instead. And I gotta break it to you, Jean-Luc, that I wouldn't know that there were 4 lights there because I don't really have the resolution. And I gotta tell you, I'm a little bit bummed about my gazillion-dollar space telescope at this point. And everybody was horrified, to be perfectly honest. This is a public relations nightmare. It took a bit of time to figure out what the problem was because, you know, they ran the gamut from, oh my gosh, didn't you check everything? Did you know, I don't know, test it? What were you doing when you said you were testing all this stuff? And no, really what it boiled down to was one of the testing apparatus pieces of equipment that you use to check the curvature of the mirror. So you grind the mirror to a certain curvature so that it sends the light where you want it to go. And one of the pieces of equipment that they would put the mirror in and use it to test what the curvature is and whether they needed to keep working on it or not, actually had a washer that was about 1 millimeter or so, maybe 2, where it wasn't supposed to have one. And that was enough to cause this problem. So yes, it passed all of the tests. It's just that the equipment was set up wrong because there was an extra washer in a place where there wasn't supposed to be one. So what do you do? Because again, this is a public relations nightmare. This is a lot of money. This is taxpayer money. And oh my gosh. Yeah. Well, if you're a creative engineer, astronomer, space scientist involved in this, you know, think smarter, not harder. And it turns out that people actually were able to think of it like, well, okay, look, people have problems seeing things clearly all the time. We measure what's wrong with their eyes, where the light's supposed to come into focus and where it actually comes into focus. And then we get them a prescription for some eyeglasses. We grind those lenses to the right curvature. We make sure that they can see out of it. Why can't you do something like that for Hubble? So people are seriously considering putting, I don't know, eyeglasses on Hubble. Yeah, that's kind of what happened. I mean, obviously it was a little more technical than that, but basically that's what they did. So they had to do a lot of tests because remember, this is in orbit now. So you've got Baltimore, the Space Telescope Science Institute in Baltimore, which is basically mission control for not only Hubble, but JWEST and several other space missions. That's where the data comes down through the pipeline and they, you know, get to calibrate stuff and kind of look and see what algorithms are being run and realize that, okay, how are we going to trick both hardware and software into giving us the measurements that we need to try and figure out what is Hubble's prescription is basically what people were asking. And it took a while, but, you know, nothing fosters ingenuity like, uh-oh, we might lose our jobs and we just wasted a gazillion taxpayer dollars. So they developed a package called COSTAR, which stands for the Corrective Optics Space Telescope Axial Replacement, which is basically fancy space goggles for the Hubble Space Telescope. So that big aluminum box that you see right there, that's actually the COSTAR goggles, if you will. That's astronauts Catherine Thornton and Thomas Akers installing it inside Hubble. Once they get it installed, and remember, again, everybody's kind of on edge here because kind of a disaster so far, right? And oh, by the way, you had to do tests from the ground that you weren't expecting to have to do these kinds of tests. And then you had to go build an optics package that you weren't expecting to have to do. And then you had to go have a servicing mission that you weren't expected to have happen just yet. And then you had to teach the astronauts how to, put eyeglasses on the Hubble Space Telescope. But they did, and everything worked. And after the repair, there's definitely 4 lights now. So you can tell for sure. All right, so crisis averted. Well, it was still a crisis, but it was a nice save. In fact, it was a pretty spectacular save. The director of the Space Telescope Science Institute in 1993, the year that it got repaired, it got its eyeglasses and got repaired, Bob Williams had one of those big ideas. It was a little bit crazy if you ask some of the people that he worked with. But he was one of those that I like to think, the reason I have a Cisco quote here that says, we're not just looking for the answers, we're actually looking for new questions. I think he was channeling a little bit of Cisco here because he had the foresight to think about all of those pictures that we would take with telescopes that showed other galaxies, but that there was a lot of empty space in between those galaxies on the pictures. And he was kind of curious as to whether that was real or not. And some people you would talk with and they would be like, well, I guess, it's not like the universe is going to be full of stuff everywhere, right? There can't be something in every single place. So you're going to expect to see some empty spots, right? Some open space. Well, maybe, maybe not. We still didn't really understand a whole lot about the large scale structure at that point and the behavior of our own universe, in fact. And in fact, some of you who know a little bit more about this are going to realize that this is actually before we even knew that the expansion rate of the universe was increasing. So at this point in time, we know that the universe is expanding, but we didn't know that the expansion rate is getting faster. We assumed it was a constant rate of expansion. So one of Bob's ideas is, hey, why don't we use this fancy space telescope to take a picture of nothing for a really long time and just see if there's really nothing there? And as you can imagine, some people, thought that was an interesting way to use taxpayer money. And others just thought, dude, that's crazy. Like, seriously, why are you going to do this? We just recovered, right, from a PR disaster. If you do this and this goes sideways, I don't know. We're not coming back from this. Like, I don't know what's going to happen. But the rumor goes that Bob Williams decided to use his director's discretionary time, which means basically every observatory, major observation facility, astronomical observation facility has a director, and usually it's pretty common to give that director some discretionary observing time on the telescope as part of their compensation package. And so it's called discretionary time because they get to do kind of whatever they want with it within reason, as long as the science proposals that have already been accepted and funded are not working at the same time. So you kind of wait for the downtime in between the other science proposals. He managed to convince some people to come along with him on this journey. And they used the Christmas break over 1994 to 1995 Christmas break. So they actually did a study to find a piece of the sky that was so boring, like seriously, the boringest piece of the sky. Why would you ever point any telescope there, let alone this gazillion-dollar space telescope that, by the way, is still on a little bit thin ice at this point in time? Why would you want to do that? And I think at this point, it's kind of like channeling Kirk. It's not that there's things that have to be unknown. It's just that you don't know them yet, right? You don't know of them yet. They're temporarily hidden, maybe not understood. So Bob and his team did that study to find a really boring piece of sky. And for those of you that care, it's actually in the handle of the Big Dipper. Apparently, the most boring piece of sky in the northern celestial hemisphere anyway. And they used the Hubble telescope in what's called snapshot mode, which quite literally means just taking snapshots over and over and over again. Anytime the telescope had downtime and was able to point to that piece of the sky, that's what they did. So they took a lot of them and then they added them up to give the effect of taking one really, really long exposure. So this is apparently what empty sky looks like. It was released to the public in January of 1995 at the American Astronomical Society meeting. I was there in the press room, like this much of my head. The side of my head was on CNN as we all stood there gawking over a 10-foot high piece of foam core with this image on it, because humans hadn't seen anything like this up to this point. Now, I need to make sure you understand what you're seeing here. So when you look at an image like this, there's a couple of things that stick out. For some people, it's these really bright star-looking things that have these spikes on them. You see the crisscross spikes? Those are called diffraction spikes. And those tell you that that object right there is a star in your own Milky Way galaxy. It's closer to you than anything else in the picture, which is why it's so much brighter and why it's bleeding out into some other pixels. And that crisscross diffraction pattern is because of the struts, the supports that actually hold the primary and the secondary mirrors in place in Hubble. And so you get this diffraction pattern. So that's a star in the Milky Way. Here's another one up here. I think there's maybe one up here at the top, and there's maybe one or two others in the picture. Any that have these little spikes on them, those are Milky Way stars that are in your way because you wanted to see way outside of the Milky Way. The problem is you're in the Milky Way, so you got to look through it, right? So there's going to be some stars in your way. So you ignore all of those. And then you need to make sure you understand that everything else in this picture, literally everything else, is a galaxy. Some of them are probably obvious. Nice fuzzy elliptical galaxies. You know, here's a spirally looking thing right here. There's a spirally looking thing right there. But look at these little dots that people just think, well, they're just funny colored pixels. They're just artifacts. No, they're galaxies. Everything else in this picture is a galaxy. In fact, there's roughly 3,000 galaxies in this picture, give or take a few. And this is like taking a picture that's a little over 4 days long. And this is a tiny piece of sky. This image is so small, you would need about 133 of them to cover up just the full moon in the sky. That's how small of a piece of sky you're looking at. So as you can imagine, people went bonkers in the good kind of way. I imagine he probably won a lot of bets. Bob probably did. I don't know the under the table details about that, but it's safe to say that nobody thought Bob was bonkers after this. And the Hubble team certainly did get serious kudos because this was a super big deal. Until somebody raised the point of, well, wait a minute. You guys did a study to find literally the crappiest piece of sky. What if you got lucky? Like, what if there's some weird thing about the universe that says when you expect it to look like crap, it looks fantastic and amazing and full of galaxies like this? And see, that seems kind of dumb, but seriously, we don't know what the rules are at this point. So one of the hallmarks of science is repeatability. So do your experiment again. So they did. Only this time they chose a piece of sky in the southern hemisphere, but they did the same thing. You know, take some time to try and pick out what's the boringest piece of sky in the southern hemisphere you'd ever want to look at and do the same thing. So this one you're seeing now ends up being called the Hubble Deep Field North at some point because this is the Hubble Deep Field South, which is pretty much the same thing. A little over 4 days, same size. Again, not quite 3,000 galaxies or so in this picture. Yeah. I think I'm convinced that it's probably going to look about the same no matter where you point. I mean, I kind of want to know what's going to happen if you pointed it at what you thought was good sky, since apparently you thought this was ugly sky or not useful sky. And because astronomers both are not good at naming things and always want to one-up each other with my picture is deeper than your picture, my picture has more galaxies than your picture. I don't know about you, but I saw empty space in pictures like this. You know, like here, there's nothing there or there or there. I don't know. Maybe you do it again, only you go deeper, like more than 4.2 days, like more pictures. So they did. And we called it the Hubble Ultra Deep Field. Yeah. Now, time-wise, Bob Williams is gone from Space Telescope. He's retired at this point. But you can see now, apparently people can't stand it. They can't wait to take more deep fields. They can't wait to figure out, how am I going to one-up this one? What am I going to do to make this one better? How many galaxies are in this picture? Are you kidding me? Look at this. This is almost 3 times as long as the pictures we had before, and there's over 3 times as many galaxies in these pictures. I think I'm convinced. You don't have to prove it to me anymore. The universe is way bigger than we thought it was, and it includes more galaxies than we thought it did. And so your idea of far and large-scale structure, again, all going to get upgraded, because we keep doing it. And please notice how extreme is written with a lowercase e and a capital X. Yeah, that's on purpose because this one goes by the HXDF for short. So yeah, please don't let astronomers name anything again. Now, a couple things I want to point out in this picture too. You notice the color in this picture is a little more blue compared to the one we had up here before. This one's a little more orange, a little more red, right? And this one's definitely more blue. There's a reason for that. I'm going to kind of get away from that for the moment, but I want to call your attention to, look how far we're looking in space, which also corresponds to a certain amount of time back early in the history of the galaxy. Remember our unit of distance, the light year? Quite literally the distance that light goes in 1 year. So it really means if I were to look at something that were 5 light years away from me, it means it took that light 5 years to get to me. So I'm seeing it as it was 5 years ago, not as it is right now. This picture right here, you are seeing this chunk of the universe as what it looked like when the universe was barely about 500,000 years old. And just for reference, the universe is about 13.8 billion with a B. That's 13.8 and then 7 more digits after that billion. Yeah. Okay. Hang with me. Notice how these two galaxy clusters have distances on the pictures, 9 and 12 billion light years away from us. So yes, that really does mean the one on the left, that light took 9 billion years to get to us. So we are seeing that as what it looked like 9 billion years ago. That is what that place in the universe looked like 9 billion years ago. And the one on the right, yeah, that's what that piece of the universe looked like 12 billion years ago. You know, when the universe was not even 2 billion years old yet. You see things that look super weird, like this weird, what is this scary green jellyfish looking galaxy thing here? Like, that's not normal. What is that? You also might notice that the ones in the right-hand one look slightly less normal than the ones on the left-hand page. And the ones in the left-hand side, they don't look exactly like, when you say galaxy, that's not really what pops into my head, right? Like, they still look a little messed up. It's because they're babies. These are baby pictures of the universe. Now, imagine, what if you could take pictures of the universe all over the whole entire sky to different depths, which would mean different times? You'd quite literally have the history of the universe in those pictures if you only knew how to read it. Yeah, this is what galactic and extragalactic astronomers do. So yeah, definitely change the game a little. And the irony here is, remember how Bob Benjamin and crew had to kind of, you know, push the envelope a little bit to justify why we wanted to take a deep field with this telescope? The irony now is we use deep fields to justify building bigger telescopes. So you actually estimate what you're going to see in a deep field with that instrument in order to convince people to let you build the instrument, which is part of the reason we got JWEST. But let's talk a little bit about JWEST. Finally launched. Christmas Day, December 2021. Oh my gosh. So it was only, you know, like, I don't know, a dozen or so years behind schedule and a gazillion dollars over budget. Literally about $10 billion is where we landed here. But it finally went, and without a hitch. And make no mistake, there were over 300 and something, I can't even remember the number, what they call single point failures, which quite literally means any one of those 300 and some odd things happened the wrong way. And this was a $10 billion piece of space trash. But everything happened exactly as it was supposed to. It worked so well, they were kind of dumbfounded when it finally was ready to start calibration observations, because they practiced so much for, what if something goes wrong? Can we try to get it back? Can we try to fix it? What if something goes wrong? That they didn't exactly practice what to do when it went right. So they had to remind themselves how to calibrate and take data. So let's look at how JWEST is actually not a replacement for Hubble, though, because that's been touted before. And in fact, the original working name for the telescope was the Next Generation Space Telescope. Now we call it JWEST for reasons that no one cares about right now. But the point is, it's not a replacement for Hubble. There's two main differences. There's a lot of differences, but two really big ones. One is that hopefully you can see here that the JWEST mirror is way bigger than the Hubble's mirror. Hubble mirror is about 2.4 meters in diameter, and JWEST is about 6.5. So the JWEST mirror gathers about 7.5 times more light than Hubble does. And it sees a different part of the spectrum. So the Hubble Space Telescope sees almost entirely visible light with just a little bit of near infrared and a little bit of the near ultraviolet. Whereas JWEST sees only infrared, and it only overlaps a teeny bit there with Hubble. And just because we can, these are to scale with the human in the picture. So yeah, this is actually, whoa, and the human just is, whoa, transporter effect. What's going on with the human? Okay, interesting. Oh, there he goes again. I have to come back to that later. Okay, the other thing I want to point out is even though JWEST sees the infrared portion of the spectrum, it doesn't see all of it. So there's actually a teeny bit of infrared radiation out here that's not covered by a telescope because Spitzer is dead. Spitzer's been gone for a while. And we actually have no telescope that can read this part of the spectrum right now. There's not even one planned for development that can read that part of the spectrum. And that's kind of a problem because the universe is expanding. And as the universe expands, the light that we see from distant objects gets shifted to longer and longer wavelengths. So we need instruments that will read these longer and longer wavelengths in the spectrum. So JWEST is going to do a pretty good job of pushing us down, way further than we were before, but we're still going to have to backfill the rest of that spectrum when we need to. But let's take a look at, hey, JWEST took a deep field too. This is its first. Yeah. This is scary amazing to me. You will notice that the stars with diffraction spikes look different. Instead of 4 spikes, there's now, what is that, 8? You've got 6 main ones and you've got the little one in the middle there. Again, those are artifacts from the way that the mirrors, the primary and secondary mirrors are supported inside the telescope. So anything with the diffraction spikes, remember, is a Milky Way star. If it doesn't have those spikes, everything else is a galaxy. And take a look at some of this stuff. Some of this stretched out, like Salvador Dali-esque stuff we got going on right here. That's not a problem. That's not an artifact in the optical system. That's an example of gravitational lensing, which is a whole nother talk all by itself. Super cool. One of the ways that we know the theory of general relativity is actually correct. Right now, though, I want to ask you to take a moment and compare the Hubble field version of this. And remember, when Hubble took this picture on the right-hand side, that was the bee's knees. That was the best that it gets. Now look what JWEST can do for us. And you also have to remember, too, these colors that you're seeing in the JWEST image are not real because it reads infrared radiation, and human eyeballs can't see infrared radiation. So we had to artificially color this one so that we would know what we're looking at. We'll come back to that in a moment, too. Some more, hey, let's play what Hubble can do versus what JWEST now can do better. Oh, my gosh. It took 11.3 days to get this type of exposure from Hubble. Here's the JWEST field of view, and they did that in not even a whole day. So yeah, this is absolutely the top tier. I don't even know what else to say about it, but here, let's just show you more pretty pictures. This is probably one of the most famous pictures from Hubble, the Pillars of Creation. And now the swipe is going to reveal the JWEST version of it. Couple of things you should pay attention to. Look how many stars you see in the background of the JWEST image that you do not in Hubble. Look how dusty the Hubble background is. And in fact, when you look at Hubble, look at all these dark spots, like really dark blobs of dust and gas that you can't really see through. Yet you can almost see all the way through it with JWEST because those longer wavelengths penetrate through the dust. So if we want to do a good job studying our universe, we got to get through that. We've got to do these kinds of observations. So we've been reliving HST's glory days. Let's do it a little bit more. And then I want to draw another parallel to JWEST.
Eminent psychologist Nicholas Humphrey has written of the biological advantage of being awestruck. How fortuitous, he says, for a species to find that its own ability to contemplate, to marvel at its own existence, has been evolutionarily advantageous. In other words, it has been biologically selected for because it informs our life with a sense of cosmic significance that makes us work harder to persist and to survive. In other words, awe has helped us survive. And a recent study out of Stanford on the subject of awe kind of validates this idea. They have found that regular incidences of awe leave residual benefits upon the individual that persist, such as increased feelings of empathy and compassion towards others, increased feelings of altruism, and increased feelings of general well-being. In this study, they defined awe as an experience of such perceptual expansion, such perceptual vastness, that you literally have to reconfigure, upgrade your mental schemata just to accommodate, just to take in the scale of the experience. This is amazing. We've all felt this before. The first time we stared upon the Grand Canyon or succumbed to the immersive power of an IMAX film. But perhaps the most exquisite account of the experience experience of awe was articulated by the brilliant Ross Anderson when writing about the Hubble Space Telescope. Pay attention. He says that the Hubble has given us nothing less than an ontological awakening, a forceful reckoning with what is, allowing us to contemplate space and time on a scale just shy of infinite. Why? He says gazing upon the famous deep field photograph literally allows us to mainline the whole of time through the optic nerve. To fit something so impossibly large to something so impossibly small. Incredible. He says through the sheer aesthetic force of its discoveries, the Hubble distilled the impossibly complex abstractions of astrophysics into these singular expressions of color and light, vindicating Keith's famous couplet, beauty is truth, truth, beauty.
It's crazy, right? I bet I've seen that 100 times and I still get chilled every time. And what about James Webb? Right? It's blowing it away, right? But something else that I want us to think about. What if someone couldn't experience that, couldn't have that experience? What if they couldn't be awestruck in that way? Maybe they've got some sort of sensory impairment. Maybe they're low vision or blind or neurodivergent in some way. Any number of myriad unique characteristics of us human beings that can make it difficult, if not outright impossible, to experience astrophysical phenomena in these traditional ways. How do we help them with that? How do we help them develop those mental models? It's supposed to be everyone's universe. Well, we're making some progress. We're not all the way there, but we're making some progress. For those that are blind or have low vision, there are actually tactile graphics that they can touch, molded like craters on the moon, molded to feel like the alignment that you get during a solar eclipse. Things like 3D printed models now are becoming all the rage. Can we take these astrophysical experiences and turn them into something you can touch? What about augmented reality? It's like, you know, VR on steroids, right? And things like even making holograms and sonifying data, which we can do now. And you're going to get a cool talk about all that stuff by Kimberly Arcan on Monday. She's an expert in this. She studies how humans perceive and comprehend data and visualization across the range of spectra from novice to experts, all kinds of astronomical data sets. So that's a cool talk. If you want to know, if you can't see it, what else could you do to try to experience it? Okay, want to leave you with another idea here. Your universe is super weird. In fact, this kind of bothers some people. Let me translate for you. See this 4.9%, this blue pie wedge right here? All of the stuff that you've just seen and everything that you could imagine in the universe only is that blue pie wedge right there. It's less than 5% of the stuff that makes up our universe. The other 95% is stuff we have absolutely no idea what it is. We have some ideas what they aren't, but they're names, dark energy and dark matter, placeholder names for things that behave certain ways. We don't really know what they are. Yeah, weird universe. Also too, get this, Einstein made a mistake. He called it his biggest blunder. In 1915, he finally published his theory of general relativity. The equations predicted, though, that the universe could not be static. It had to either expand or contract. In 1915, we didn't know the universe was expanding. In fact, in 1915, it was accepted that the universe was static. It was neither expanding nor contracting. And then, you know, he solves these equations and realizes, oop, this is wrong, but he can't figure out what's wrong with it. So he inserts a fudge factor, which comes to be known as the cosmological constant. It was the thing that made the universe balance out so that it wasn't expanding or contracting. It had to be steady because, you know, it was, right? Oops, actually in 1929, not so much. That's when Hubble and his team discovered that the universe was actually expanding. So guess what? That fudge factor you put back in, you didn't need it because, you know, the universe isn't static. Okay, but then wait, you got to go all the way to 1998 before you realize Einstein actually got it right, but for the wrong reason. We discovered that the expansion of the universe is accelerating. It's speeding up. So we put back in the fudge factor. We now sometimes call it the dark energy term, the thing that repels gravity and causes the expansion to speed up. But you shouldn't be afraid of mistakes. Einstein was bummed, super bummed, according to what you read about it. You should wear those mistakes like badges of honor. Mistakes and null results are just as valuable as the successes that you perceive. We've talked about pretty much everything on this page, but where do you go from here? Because we need to keep going. Like, what's coming down here after, James Webb isn't future anymore, because it's now, because it is, right? So what's the next big idea? What's coming after this? Just pause to remind you, Star Trek was a big idea too, especially in 1966, right? From the storylines that it tackled all the way right down to every single individual in that cast. So what's next for us? What's our next big idea? The Nancy Grace Roman Space Telescope in 2027. The Vera Rubin Observatory comes online later this year with the biggest CCD camera ever made for astronomical purposes. It will image the entire southern hemisphere sky once, about every 3 nights, for 10 years. It will generate 20 terabytes of data. That's 20 trillion bytes of data every single night for the next 10 years. That's over 60 petabytes, 60 quadrillion bytes worth of data. So what's next? I don't know, AI, machine learning? Any of you? Because you could be a part of it. Because we need all of you, of every ability and every desire and every want to know about everything to do with your universe. Everybody's got a role to play. I dare you. I dare you to do better. What's next? Thank you.